Never before has there been such an incredibly large focus on something quite so small as quantum mechanics. For those working in the field, and for many watching on from the sidelines, this is the bleeding edge of modern research. We've covered the Barrow scale in past videos before, a kind of reverse Kardashev scale where emphasis is on gaining control of increasingly small entities rather than big. But while there are other ways of approaching the subatomic realm, humanity does appear determined to complete the Barrow scale, and quickly. So much so that even the concept of things like nuclear fusion or gene editing are thoroughly tried and tested today. Now we're already moving on to ideas and structures that are even more fundamental to reality: elementary particles and light itself. Quantum light is a relatively new focus in quantum physics. It involves studying the photons of light at the subatomic level, often with the end goal of controlling them to reveal more about the world around us. While science has a fairly solid grip on classical physics on a macro level, it gradually loses that grip the further down into the quantum realm we delve. Bizarre mysteries such as quantum entanglement rule the roost down here, as it's so often said that physics breaks down when we reach the quantum stage. But that's why it's so important for scientists to try and harness some control of it, hopefully via quantum light. According to a new study published in February 2023 in the journal Nature Physics and conducted by an international team led out of Cambridge University, we might now have devised a way to achieve the quantum light we need. The method would involve directing strong lasers at specifically built emitters to produce higher frequency light as an output. Researchers might then be able to study that output light in a structured way, applying some form of order to the quantum fluctuations that guide it. The process has yet to be carried out, so the quantum light it could produce is therefore still theoretical. But the team behind it, including the study leads, Dr. Andrea Pizzi and Alexei Gorlich, are confident that it will work. According to an accompanying press release issued by Cambridge University, the technique, quote, could be used to engineer the quantum optical structure of X-rays, end quote. More broadly, it's thought that by harnessing quantum light, science should be able to see the previously unseeable better than it ever has done before. The work could lead to major advances in microscopy, the study of materials, including biological materials, and the development of quantum computing. At this stage, it's not clear exactly how the approach will reveal itself, but to some degree, it should be as though it zooms in on and slows down subatomic matter. That slowing down has everything to do with the strange field of attoscience, otherwise known as attosecond physics. An attosecond is 1/quintillionth of a standard second. It's one of the very smallest units of time that's out there, and it applies to things like how quickly a photon moves across a hydrogen atom, or how quickly electrons move between atoms. In the quest for quantum light, there's a push to generate laser pulses that come and go in attoseconds as well, with just 43 attoseconds being the record so far. Again, as with most everything else in this field of study, such staggeringly fast pulses of light are undetectable by us on a classical macro level. But if we could find a way to not only record them, but control them through the manipulation of quantum light, then suddenly it's as though we tap into a different state or a different frequency of reality. One potential final destination here is to be able to view atomic and subatomic structures, now bathed in quantum light, in a discernible and appreciable way. This in turn could lead to real-time control of subatomic matter. It would be as though we were capable of rearranging, redirecting, and/or refocusing the most fundamental elemental building blocks of the world around us. As such, this work is intrinsically linked with quantum computing. Today, according to multiple studies, reports, and early developments, we stand on the very brink of a quantum computing age, which will very quickly leave our traditional computing powers in its wake. At the heart of it are quantum bits, or qubits, which vastly improve on the zeros and ones of binary bits to become both at the same time, thereby dramatically increasing our process capacity. It's predicted that a quantum computer will one day be able to complete tasks in just a few minutes that would have previously taken even our very best supercomputers days, weeks, years, or even decades to perform. In our pursuit of knowledge, quantum computing is data diving at unimaginable speed and efficiency. And while in itself the advent of quantum computing doesn't solely rely on the channeling of quantum light, the latter could certainly accelerate the former into being. But still, this latest study is just one in an ever-lengthening list of research projects determined to make better sense of particle and quantum physics. While the likes of CERN on the Franco-Swiss border and Fermilab in Illinois, US tend to dominate the headlines, there are a growing number of theories and unique approaches that are being practiced. In September 2022, one multi-authored study showed how AI machine learning could be applied to quantum problems to potentially reduce hundreds of thousands of endless equations down to just 3 or 4. This kind of extreme simplification of the process could prove vital as we move forward with research all across the board, including with the generation of quantum light. Meanwhile, and as we explored in another recent video, there are some suggestions, such as the theory of biocentrism, that quantum processes might even be guiding life and death. So while it's true that not everything in theoretical science is geared toward achieving immortality, there are some who believe that our gaining a better understanding of it could ultimately lead us to reinterpreting our own temporality and humanity. Again, the most recent investigations into quantum light, into how to harness it, and what it might be used for, aren't explicitly detailed in anything like the Barrow scale, but as the Barrow scale is otherwise labeled as the scale of micro-dimensional mastery, it's clear that there are links to be found. Science's want to unlock quantum light is tied up in our emerging realization that by controlling very small things, we really might become much more powerful than we'd ever previously thought possible. This was John Barrow's way of thinking too. But what's your verdict? Are we right to direct so much attention and resources towards these types of experiments? Are we headed in the right direction by continually trying to hone in on smaller and smaller scales of stuff? And how do you envisage the future if we ever do cast quantum light through everything we see? On the one hand, this is an absurdly exciting time for science. On the other, there is a disturbing unease to be felt in the realization that truly nothing is permanent once we start stripping it back to, and even beyond, the atoms that make it. For now, for better or for worse, the first steps along our quantum journey have already been taken. We're splitting atoms, splicing genes, and combining molecules in a bid to create better and more efficient materials, in an attempt to gain a purer sense of how the world, how existence, really works. It's a revolution that's being felt in physics, engineering, medicine, and computing. But for the most part, most of us are at least still viewing life in much the same way. Our comprehension of reality is shifting, however, and to make the leap from now to the future, it could well be quantum light that's illuminating our path.